Assalamualaikum and hi everyone, this is Dr. Shazira. In this video, we are going to be discussing the boundary value problem using the finite difference method. Consider this second order boundary value problem in the form of y double prime plus p of x. So p is a function, but in the problem it could be constant as well. P of x times y prime plus q times y equals r, in the function in terms of x, where your x is from a to b. So you know the length of your x is b minus a. All right, and you are supposed to be given two boundary conditions. The first one is supposed to be at the left boundary and another one is at the right boundary, of course. So this is your left boundary and this is right boundary. So by the finite difference method, it means that what we are going to do here is we are going to replace the derivative terms with the finite difference formula. So in this BVP here, so you can see this is the derivative term, y double prime, and then you have y prime, and you also can see the derivative in the boundary condition. So you have y prime a and y prime b. So we need to replace the four terms that you can see in the box over there with the finite difference formula. What are the finite difference formula? So before this, I believe you have learned about the numerical differentiation, where you have few types of finite difference formula. If you can recall, you have the backward formula, forward formula, centered difference formula, and so on and so forth. For the first order, second order, I think you also have the third order, fourth order, before this. But in our discussion here, we only have up to the second order. So it means we are going to replace y prime and y double prime with the finite difference formula. So for discussion, we will only consider the centered difference formula. So what do you have in the centered difference formula for first derivative? So y prime, your first derivative, by the finite difference formula, specifically centered difference formula. So it is yi plus 1 minus yi minus 1 over 2h. So that is y prime. And then yi double prime is given by yi minus 1 minus 2yi plus yi plus 1 over h square. So we will replace y double prime and y prime in our BVP here, the problem here, with these two finite difference formula. And the procedure, steps of solution. So basically you have 1 to 7 here. All right, so basically the first step, we will divide our interval a and b into n subinterval, with a step size of h. And then we sketch the grid of solution. We discretize the boundary. Discretize here means you replace the derivative term in your boundary condition with the centered difference formula. And then we proceed with the discretization of the differential equation of the ODE. We replace y double prime and y prime in our equation, also with the centered difference formula. And then we will have our ODE in a finite difference form, and then after that we will see how we will form a linear system. And finally, by solving the linear system ay equals b, then we'll get y. Because by solving the boundary value problem here, so basically we want to get the value of y. So at the end, when you solve ay equals b here, so you are supposed to know, okay, the value of y that you wish to get, okay, at the first place. All right, so I will explain all the procedure here, steps 1 to 7 here, um, um, based on the example, okay, so that you can see clearly and it is hopefully easier for you to understand, okay, based on the example. All right. Consider this example, okay, this BVP here. So you need to solve this BVP here using finite difference method with h equals 0.5. Okay, so h is basically the step size of your x, okay, and then you are given the boundary condition. So you can see at the left boundary you have y0 equals 1, and then at the right you have y1 plus y prime 1 equals 0.5. Okay, so you can see here on the left boundary, okay, so this is your left boundary, there's no derivative involved, so it's okay. Okay, there's no derivative involved, but somehow at the right boundary you can see you have the derivative term y1 plus y prime 1. Okay, so the derivative term could be in both boundaries, or it could be, you know, at one of the boundaries, okay, or it can be, you know, no derivative at all at both boundaries. Okay. All right, so your first step is to draw the grid of solution. All right, so your first value of x, okay, we denote as x naught. So based on the boundary condition, we know that our x naught is 0. Okay, so you can see by looking at your left boundary, so you have y0 equals 1. So it means when x is 0, the value of y is 1. All right, so when x is x naught, the corresponding y is supposed to be with the same subscript as well. So you have y naught. So in this case, y naught equals 1. So you can put straight away y naught equals 1 because you can see, you know, based on the given boundary condition at the left, okay, at the left boundary. Okay, and then your h is 0.5. Okay, h is the step size of x, so it means that somewhere here you will have your x1. So this is 0.5. Okay, and then you are going to have another point, okay, because your right boundary is at x equals 1. So you can see based on the right boundary condition, y1 plus y prime 1. So you know the right point is 1, okay, and then your left point is 0 somehow. Okay, so you will have x2, so this is 1. Okay, so it depends, okay, it depends on your boundary condition. So if you have y2, for example, so it means you need to proceed to x3 and x4. Okay, but for this one you only stop up to x2. And then you can remark here the corresponding y here should be y1. Okay, we don't know what is y1 yet, and here you have your y2. Okay, so careful here, your y2 is not 0.5. Okay, so you can see from the right here, the right condition, y1 plus y prime 1 equals 0.5. So y2 here is not straight away 0.5. So this is wrong if you write like that. Okay, because 0.5 is basically y1 plus y prime 1. It is not only y1. Okay, but at the left boundary, it is okay to write 1 here because y0 equals 1. Okay, you don't have the derivative term at the left boundary. So y0 equals 1, but at the right boundary, y2 is basically unknown at this moment. Okay, so we are going to find out what is our y1 and y2 basically. Okay, that is your first step. So second step is to discretize the boundary condition. Discretize the boundary condition that contains the derivative. So you discretize, or basically you replace the derivative term in your boundary condition with the finite difference formula. So you only do this at the boundary condition that contain the derivative. Okay, so it means that for this example, for the left boundary, you don't have to do anything, because at the left boundary here, the boundary condition at the left, you don't have the derivative term. You only discretize the boundary condition that contains the derivative. So you only discretize the right boundary in this case. Okay, but if your left boundary condition, if you also have the derivative term, then you need to discretize both. Okay, but for this one, we only discretize for the right boundary only. All right, so I'm going to write down one more time. Okay, our boundary condition, our right boundary condition is y1, okay, plus y prime 1 equals 0.5. Okay, so in terms of subscript notation, so y1 is basically y sub 2, because y1 is basically the value of y when x is 1. Okay, so based on your grid here, so x is 1 is here, and the corresponding y is y2. So y1 in different notation, it is y sub 2. Okay, so y prime 1, so the same, this is y2 prime, okay, equals 0.5. Okay, so now our intention, our concern now is that guy, y2 prime. Okay, because we want to replace that term with the finite difference formula. Okay, so if you can recall, the yi prime in general is given by yi plus 1 minus yi minus 1 over 2h. Okay, so now if we map y2 prime here with the yi prime, so we know that our I is 2. Okay, so what happened is now you will have y2 plus, so y2 prime now will be replaced with the finite difference formula. Okay, so based on the term that you can see here, okay, you map with the y2 prime, so you know your I equals 2. So at the right hand side here, you have y3 minus y1 over 2h equals 0.5. Okay, that is clear. Okay, so now if we isolate y3 minus y1 over 2h at the left hand side, then you will have 0.5 minus y2. Okay, and then we rearrange the equation so that we can isolate y3 at the left. Okay, so y3 equals since you know your h is 0.5, so you can plug in, okay, into the equation at the left. Okay, so you have y3 equals 0.5 minus y2 plus y1 at the end. Okay, so the idea here is to isolate y3. So you isolate the term that you don't have in your grid of solution. Okay, so you have y0, y1, y2 only. Okay, so y3 is somewhere here, is out of your grid here. So we take out that term, y3 equals 0.5 minus y2 plus y1. So later on, okay, in the next calculation, you will see, you will use this y3 here. Whenever you encounter the y3 term in your calculation, you will replace with the 0.5 minus y2 plus y1. Okay, but for now, we are going to, just, put this one as equation. I'm going to assume this is E. Okay, so later on, we'll refer to this y3. Okay, so that is your step number 2. So step number 3 is to discretize the equation now, the ordinary differential equation. All right, so we are going to use these two finite difference formula, okay, to replace the derivative term in our ODE. So our ODE is this equation here, y double prime plus xy prime plus 2y equals exponent of 2x. So y double prime here, so you are going to replace with the finite difference formula as well as for y prime here. So see what happened to your equation. So firstly, you have y double prime. So you are going to replace with this term here, okay, expression at the right. over there. So the ODE becomes, this is what you are going to have. Okay, so basically this is your y double prime plus x. Okay, so you just replace x with the x sub I, because we have discretized our x value, okay, from a to b into sub interval. So we use the notation x sub I here, and this is your y prime, and this is plus 2y. Okay, so you replace with y sub I equals to, at the right hand side you have exponent of 2x sub I. Okay, so now this is already in a finite difference form. Okay, your ODE in a finite difference form, but we want to simplify this expression, okay, as simple as possible, because the simpler the equation that you have, so your next calculation would be much more easier. Okay, so what we can do here, we want to get rid of the fraction. We don't like the fraction. Okay, so what we can do here, we can multiply both sides, okay, with 2h squared. Okay, so that we can get rid of the fraction. Okay, get rid of the h square at the bottom. Okay, so by that, what do we have now? So we will have 2 at the top here. Okay, but in the bracket we still have that expression in the bracket. Okay, but somehow at the bottom we can cancel out h squared. Okay, plus in the middle, x remains. Okay, but somehow h squared and h, okay, you can simplify. So you have 2 and 2 as well can be simplified. So you only have h xi here, and this is yi plus 1 minus yi minus 1. And then you have here 4 h square yi equals 2 h square exponent of 2xi. Okay, and then you can see you have few times of yi minus 1. So you have here yi minus 1, this is another yi minus 1, as well as yi here, this is another yi, and also yi plus 1. So it means that what we can do here, we can factor out. Okay, we can factor out the same term so that we can, you know, get shorter expression. All right. So if we take out our yi minus 1, and then in the bracket you are going to have 2 minus h xi. Okay, and then in the middle we put yi, and then we have negative 4. Okay, and then yi, okay, plus 4h squared. Okay, and then we factor out yi plus 1, then in the bracket we have 2, and then another 1 plus h xi. Okay, at the right hand side remains, so 2h square exponent of 2xi, but here we know our h is 0.5, so that now we can simplify further. So if we rearrange, okay, put the coefficient first, so it means you are going to have 2 minus 0.5 xi, okay, which is the coefficient of yi minus 1, and then you will have, you can simplify here, negative 4 plus 4 times 0.5 square, that will gives you negative 3, so then multiply with the yi, and then you will have 2 plus 0.5x, okay, so 2 plus 0.5 xi, and then here you have yi plus 1. At the right hand side you have 2 times 0.5 square, that will gives you 0.5 exponent of 2xi. Okay, so and then our I here is 1 and 2. So I here basically depends on your unknowns. Okay, back to your step number 1. So you can see your unknowns are y1 and y2. Okay, so imagine this is your y sub I, so it means your I, okay, is 1 and 2. Okay, so in terms of molecule diagram or computational molecule, okay, molecule diagram, So the equation that you have over there, so this is actually your ODE in a finite difference form. Okay, in terms of molecule diagram, you have yi minus 1 at the left. In the middle, you have yi. At the right, you have yi plus 1. So this is equal. Okay, so the relation is, okay, so yi minus 1 here. So the coefficient we put at the top here. So this is the coefficient xi. And here you have minus, okay, and this is 3, or basically you can put plus here, but somewhere here you need to put negative 3, okay, and then this is yi, this is yi plus 1, the coefficient is 2 plus 0.5 xi, at the right hand side you have 0.5 exponent to xi, okay, where I is 1 and 2. Alright, so that is your third step. Okay, fourth step is to form a linear system. Okay, a linear system based on the equation that you can see here. Okay, based on your molecule diagram here. Okay, so we will start with I equals 1. So you can see when I equals 1, so what happened is when I equals 1, so see based on this molecule diagram here, so this yi minus 1 here will be y naught, y0, and this is y1 and this is y2. And see what happened to the coefficient here, you are going to be using x1 somehow because your I here is 1, so x1, okay, and here, okay, you are going to put x1 at the right hand side here, you also need x1. So basically when I equals 1, you have you need to use x1, okay, which you can see in your grid, x1 is 0.5, so you are going to use that. Okay, so now what happened to your equation, okay, based on the molecule diagram? So you put the coefficient first, so you are going to do 2 minus 0.5 times 0.5 because your x1 here is 0.5. So that will gives you 1.75 y naught. Okay, minus 3. Okay, so see in the middle. Okay, negative 3y 1. Okay, so here the relation here is plus, right? Alright, now, so here, the third term, okay, you have plus here. So the coefficient is, so you will do 2 plus 0.5 times x1 is 0.5. So 2 plus 0.5 times 0.5. So you will have 2.25, okay? That is the coefficient for y2, okay? 1 plus 1. At the right hand side, okay, so the same thing, you can plug in x1 over there, over here as 0.5, so you have a known value basically at the right hand side. Okay, so multiply all those 0.5 and the exponent term, so you will have 1.3591. Okay, so that is your first equation. But here you can see so maybe you want to put here, so your aim is actually to get your y1 and y2. So based on the first equation that you obtain here, so you can see your unknown is y1 and y2, but somehow in the equation you have y0. Okay, so if you can recall, if you go back to your first step, okay, in your grid, so you can see you already know your y naught somehow. Okay, your y naught is 1. Okay, so this is your left boundary. So what you can do here, you can replace that value immediately. So y naught here is 1. Okay, so now 1.75 times 1, okay, is a known value, so you put together with the right hand side because our intention is to form ay equals b. Okay, so term with the unknown you must put at the left, Okay, the known value, you put all of them at the right hand side. Okay, so by that you are going to have at the left negative 3y1 plus 2.25y2. So at the right hand side, okay, you will have negative 0.3909. So this is your first equation. Okay, remark as equation 1. Alright, so that is when I equals 1. So similarly, you will proceed with I equals 2, and then you can see now, based on this molecule diagram, when I equals 2, this guy here will be y1, and this is y2, and this guy here will be y3. And the coefficient, okay, so you will use now xi here will be x2, okay, because your I is 2. So your x2, okay, based on your grid, so x2 is 1 somehow. Okay, so the coefficient will be 2 minus 0.5 times 1. So here you are going to have 1.5 y, 1, minus, in the middle you have negative 3, so minus 3 y2, plus, so the coefficient of y3 here, okay, 2 plus 0.5 times 1. So you have 2.5 y3 equals, at the right hand side you can replace x2 with 1, so you only have 0.5 times exponent of 2, so that value is 3.6945. Okay, so in this equation, all of the y terms that you can see at the left, they are all one of the y's, okay, is basically can be replaced. Okay, your aim is y1 and y2, but somehow you can see y3 here, which is out of your grid. Okay, there's no y3 in your grid. So if you can recall, okay, in your grid solution here, there's no y3. So you need to know, okay, that y3 must be replaced with something that you have. Okay, so what is y3? So that is the step that you have done in step 2 here. So this is the use of y3. So you will replace the y3 with this expression. Okay, so that you can see you have y2 and y1, which is the unknown that you have somehow in your grid. Okay, so what we are going to do here, so y3 here replace with a. Okay, so I put here a. Okay, so it means here you are going to have 1.5 y1 minus 3 y2 plus 2.5. Okay, so the expression of a just now is 0.5 minus y2 plus y1. At the right hand side you have 3.6945, and then you can simplify further, because now you can see you have y2 here, this is another y2, and you have y1, which can be simplified with that y1. Okay, so simplify things here and there, plus minus here and there, so you are supposed to come out with 4y1 minus 5.5 y2 equals, so you can see this guy here, when you multiply 2.5 and 0.5, and then you will have known value which need to be put together with the 3.6 here at the right hand side. Okay, so it will gives you 2.4445. Okay, so now you can put that equation as equation 2. Alright, so what you can see from equation 1 and 2, so we just stop at 2 equations here because we are done with our I here. I equals 1 and 2 only. So based on 1 and 2, so therefore you can see in the form of matrix. Okay, this is optional. You can write if you want. So in terms of the matrix, then you can see, if you take out your unknown, which is only y1 and y2 in this case, okay, so based on the equation, so at the right hand side you have negative 0.3909 from the first equation. From the second equation, this is 2.4445. So the coefficient matrix then will be negative 3. So this is based on the first equation. and the coefficient of y2 is 2.25, and then from the second equation we have 4 and negative 5.5. Okay, so our intention is to find the solution for our y, right? So you solve the system. Okay, so last step is basically solving the system. Okay, but for this example, this is just 2 by 2. Okay, 2 by 2 system which can be solved easily by calculator. So for this one, you have step number 5, solve the system. Okay, solve the system. So I just put here by calculator. Okay, so by calculator, y1 equals negative 0.4467 and y2 equals negative 0.7693. Okay, so that's it. Alright, so those are the final answers. Okay, so but sometimes the question asks you to solve the system using specific method. Okay, especially when you have higher system here. Okay, you may end up, for example, with 4 by 4 system. Okay, so somewhere here when you want to solve the system, sometimes the question asks you to do like Thomas algorithm or maybe Gauss-Seidel, Jacobi. So it depends. Okay, it depends on the problem. But if the question didn't ask for any specific method, okay, to solve the system, then basically you can just use your calculator. Yeah, especially if you only have 2 by 2 or 3 by 3. Okay, or in fact, yeah, if it is 4 by 4, you also can use your calculator. But if the question asks for the specific method, then you need to follow. Alright, so that's basically how you solve the BVP using finite difference method.